Let us now discuss the equivalent circuit of induction motor. So what is happening here? The current in stator winding, when you supply current to the stator winding, it will induce current in rotor winding. So from this, can you remember of another machine which has a kind of similar operation? It is the transformer, right? So what happens in a transformer? There will be a primary winding, we give current, this will induce a voltage in the secondary winding, and if there is a load connected, then current will flow. That means a closed path. If it is present on the secondary side, then the current will flow. Similar thing is happening here. We have, instead of primary winding, this is primary. Instead of primary winding, you have the stator winding, and instead of secondary winding, you have the rotor winding. And what is the other difference? The other difference is that this is a rotating machine, whereas a transformer is a static machine, it is not moving. So now what we can do is, we can take the equivalent circuit of the transformer, and from that we can develop the equivalent circuit of the induction motor as well, by including these changes. This is the major change, a rotating machine. This is just the name, right? Instead of primary we write stator winding, instead of secondary we write rotor winding. But how to incorporate this rotating characteristic into the equivalent circuit? First we will take the exact equivalent circuit of the transformer, and from there we can build the induction motor circuit, okay, of transformer. So remember, this is the transformer, not the induction motor, okay. So we will have a resistance and an inductor in series, and there will be a resistance and inductor in parallel, series parameters and shunt parameters. And then we are going to have the winding. This is the secondary side, and similarly you have the series parameters here, okay. So here this is R1 and JX1, which is the parameters of the winding, the resistance of the winding and the leakage reactance. What about these shunt parameters? These are the core loss components, a resistive and a inductive component. That means they exist because of the magnetic core around which the windings are wound. And finally we have here the series parameters R2 and JX2. These are the resistance and the inductance of the secondary side winding. And what is this? This is the ideal transformer part. We are discussing the exact equivalent circuit, right? So this will be the internal voltage, the induced voltage on the primary and secondary side. And these are the terminal voltages, V1 and V2. You can also use a subscript P or S. P means primary, S means secondary. So this was the exact equivalent circuit of transformer that we discussed. So let us see how this will be in the induction machine. The R1 in the transformer is the primary winding resistance. For induction machine also it is the same thing. Instead of primary winding there is going to be stator winding. So R1 is the stator winding resistance. And what about X1? This is the primary winding leakage reactance. Similarly, here also for the induction motor also we will have the same parameter X1, which is the stator winding leakage reactance. Next what we have, RC and XM, okay. So what is RC? This is the core loss component, that means due to hysteresis and eddy current losses. Similarly, you are going to have the same thing here. This is also a machine which has a magnetic core, so there will be hysteresis and eddy current losses here as well. So that is what is this RC. Now what about XM? This is the reactance which is required to establish flux, magnetic flux. Same thing will be present here as well. But one important thing that you need to know here with respect to Xm is the comparison between the Xm of the transformer and of the induction motor. So what is happening for the transformer? How will the core be? This is the core, right? And how are the windings? These are the windings, right? You can see that there is no air gap for the flux, right? Because the flux is going along this core. It is not encountering any air gap. But for a induction motor, this is different. You're going to have the rotor here and this is the stator. Now the windings, the rotor windings are on this and the stator windings are on the stator. Okay. So this is the stator and this is the rotor. Now the magnetic flux has to pass through this air gap. Between the stator and the rotor, there is no magnetic core, there is air gap. And the flux has to pass through this air gap. Okay. So what will happen? What is the result of this is that the magnetic flux path will experience more reluctance. So this you can write, air gap will lead to more reluctance. So what is the result of more reluctance? You remember the analogy between magnetic and electric circuits. Reluctance is same as resistance. Flux is same as current and MMF is same as voltage. What is MMF? MMF is nothing but N into I, number of turns into current. So now more reluctance is required in order to produce the same amount of flux. That means in comparison to transformer and induction machine. Same flux if you want to produce in an induction machine as you have produced in a transformer, then because of the more reluctance, it will require more MMF. Okay. So that means it will draw higher magnetizing current. Higher, you can write draws higher magnetizing current. So this is the important thing that you have to remember. Now, what is the effect of this on the magnetizing reactance? That means in comparison to transformer, how will the induction motor magnetizing reactance be? Since it is drawing higher magnetizing current as compared to a transformer for a given supply voltage, this means that the reactance should be lower. So the induction motor will have lesser magnetizing reactance. So this is all about the stator side. Now the rotor side we will discuss separately. The rotor circuit model. So the first question here is, why are we discussing this separately? We've already discussed before that the frequency of the rotor currents, Fr if you take, this is equal to S into Fe, where S is the slip, Fe is the electrical frequency of stator currents. Okay, you can write Fr also. This is the electrical frequency of rotor currents. So that means the frequency of the rotor current, it is not constant, it is varying with respect to the slip. Slip is nothing but it gives an indicator of speed, right? So that means the frequency is dependent on the speed of the induction motor. Okay, but in a transformer there is no difference. Whatever frequency is there in the primary side, the same frequency will appear on the secondary side. But here the frequency is not the same. That is why we will discuss the rotor circuit model differently and then try to incorporate the model along with the stator model. Okay, the stator side. Now we know that the induced voltage, it depends on what? Relative velocity. So when the motor is running at synchronous speed, let us say, therefore when n is equal to ns, that means motor is running at synchronous speed. Then the induced voltage will be what? It will be 0. When n is equal to 0, that means in the locked rotor, that means we are seeing to it that the rotor is not rotating despite the presence of rotating magnetic field and everything. In this case, the induced voltage will be the highest. Let us take this induced voltage to be E R naught. The subscript R for rotor induced voltage and naught just to represent that it is the induced voltage at locked rotor condition. What is the slip at this point? S is equal to 0. What is the slip at this point? It is equal to 1. So you can see that the induced voltage is proportional to the slip. Therefore, at any slip S, that means any slip S between the 0 speed and synchronous speed, the rotor induced voltage, if you take as ER, then this will be equal to S times ER naught. Okay. So this is the important expression. When speed keeps increasing, the slip keeps falling. The highest value of S is 1, which is when you get ER naught. The rotor induced voltage will be equal to ER naught. And as slip keeps falling, when the speed increases, the rotor induced voltage will keep falling. Okay. So now you can draw the rotor circuit. You will have the induced voltage ER, and this will drive the rotor currents, and this will experience, what will it experience? The rotor current, it will experience the resistance of the winding, which we will take as RR, and it will also exhibit the reactance XR. Okay. So this is the rotor side circuit. But what are the values? Where ER is equal to S times ER naught. And what about XR? We know that the reactance will be equal to the angular frequency into the inductance. So this you can write rotor frequency, and this is the rotor inductance. So that means the reactance is a frequency dependent component. How can we express it in terms of the slip? The angular frequency you can write as 2 pi FR into LR. Now FR you can write as S into FE. So you can take S common and you can get 2 pi FE into LR. So once again, what will be this term? This is the reactance that is present at locked rotor condition. Okay, that means when the induced voltage is ER naught. So we will express XR as S times XR naught. Okay, where XR naught is reactance offered at locked rotor condition. Now what about the rotor current IR? IR you can express as ER divided by RR plus JXR, right? Simply the voltage by impedance. So now you can write this as S times ER naught divided by the resistance plus J into S times the XR naught, locked rotor reactance. Okay. So this further it can be written as ER naught divided by RR by S plus JXR naught. Okay. Now using this equation, how we can draw the rotor circuit? You can have the voltage term as ER naught, the resistance term as RR by S, and the inductance can write as JXR naught, the reactance. In this circuit, what will be the current? The same IR current will flow. Okay. So this circuit and this circuit represent the one and the same circuit. The rotor circuit you can represent as this also, as this also. But why is this important? you can see here that the voltage term, this is independent of the slip or the speed, okay. Whereas here if you can see, the voltage term is ER, which is dependent on the speed, okay. So that is why we have acquired this form. Now in this form you can see that the reactance is also same, it is independent of the speed. The only term which is dependent on speed is now the resistance. So now we can combine both the stator and rotor circuits to get the actual final equivalent circuit, okay. So this will be just like transformer only with the slight differences in the parameters. These are the core components. This is R1, JX1, RC and JXM, okay. Instead of the subscript 1, you can also use S, okay. S means stator side. And the rotor side, how we can draw? First we will draw the ideal transformer, then we can refer onto the stator side, okay. So this is ideal transformer. Here what you are going to have, the rotor voltage. This is ER, or you can also write as E2. Usually what you do is, since R1, X1 if you are using, then the secondary side also you use numericals only. If you are using S subscript, then you use the subscript R. It will avoid any confusion, okay. So you are going to have the resistance and the inductance. Now what is the value of the resistance and inductance? This also, the parameters you can write as S times ER naught. What about the resistance? R2 by S or RR by S, okay. Finally this also, JX2 or JXR. So now if we want to remove this ideal transformer, then we have to refer all of these parameters onto the primary side or the stator side. So how to do that? The stator side will remain same. So you can draw, this is R1, X1 are the shunt parameters. Now this is the voltage on the primary side. So this will be E1, which will be equal to the secondary voltage referred to the primary side. So we represent it as E2 dash. If there is a transformer, we write E2. So we are ignoring ER now, okay. Subscript R you forget. We will use 2 only because on the primary side we are using 1. So this E2 voltage, if we are referring on to the primary side, it will become E2 dash and that will be equal to E1. So how do you refer a parameter? E2 dash, this is when E2 is given, how to get E2 dash? This will be equal to N1 by N2 into E2, okay. What is N1 and N2? N1 is the number of turns of the stator winding, N2 is number of turns of the rotor winding. Just like transformer, nothing different. And here R2 dash by S, and finally the inductance is JX2 dash. So since we have referred all of these parameters to the stator side, we are using the dash, okay. But what is it equal to? R2 dash is equal to N1 by N2 whole square into R2. X2 dash also, similarly you can write N1 by N2 whole square into X2, okay. Now what about the rotor current? The current also you can write, this is going to be IR dash. Initially what was the current that is flowing through the rotor side? Simply IR. Now that we have referred to the stator side, we will write it as IR dash. So what will be the relation between IR dash and IR? This will be N2 by N1 into IR, okay. The rest of the parameters are as it is. This is R1, JX1, RC and JXM. This also you can write as I2 dash, okay, for uniformity. What about the stator side current? This you will represent as I1. So this is the final equivalent circuit of the induction motor. So this is the final equivalent circuit. But sometimes while doing problems and in certain analysis, we ignore this RC. Okay. This is a valid enough approximation and it will make the analysis much simpler. Okay. So these are, in any problem, in fact, certain approximations are made to make the problem much easier to analyze. Okay. So here the parameters are R1, Jx1, this will be Jxm, R2 dash by S, Jx2 dash, and the currents are I2 dash and I1. What about the voltage? E1 is equal to E2 dash. So this is the approximate equivalent circuit. Now one more final thing that you need to know is the induced voltage. We have seen E1, E2 dash in the equivalent circuit, but what is the value of it? What is its formula? Okay. So the RMS induced voltage will be similar to the transformer. This is equal to per phase. Okay. Remember, it is for per phase since it is 3 phase. The machine is 3 phase. So this is equal to root 2 into pi into F phi n, where what is all of these parameters? Where F is the frequency, the electrical frequency, phi is the maximum or the peak flux, and finally n is the number of turns. If you take number of turns on stator side, you will get stator induced voltage. If you take number of sides on the rotor side, then you will get rotor induced voltage. Okay.